Okay, last chapter, which is really about thermodynamic equilibria. In other words, we said there's two aspects of chemical reactions: how fast you get to equilibria and how much product you get at equilibria. We're going to talk about how much product, and we're going to take a look at that when we talk about equilibria in terms of environment. We're going to take a look at a water environment. And really, when you look at the chapters for thermodynamic equilibria in this textbook, we're going to combine chapters 22, 23, and 24. And I'm going to take a narrow overview of it. And really what we're just looking at is three different aspects of equilibria in a water environment. Chapter 22, the end of it, talks about general equilibria and how it relates to kinetics, where chapter 23 and 24 talk about acids and bases and salts and the calculations involved with it. So we're going to go that approach. All right, so at the end of chapter 22, we left off. Once a reaction reaches equilibria, relationship among the concentration of reactants and products can be determined. And I said that that was the equilibria constant, what they call capital K, or generalized, they call it K with a little EQ, which means products over reactants for any generalized equation. So we're going to do concentration of our products over concentration of our reactants. Now, those can be raised to a power. So we'll say products raised to the X, reactants raised to the Y, but it's products over reactants, and it's going to come out to be some value, some number, which describes what's called the position of the equilibria. Now, pardon me, in the other chapters, in the other two chapters, 23 and 24, they talk about, for instance, Ka. And all Ka is reactants over products when we're dealing with acids producing ions. And then they're going to talk about Kb, which is, I said reactants over products. Products over reactants for acids produces ions. For Kb, it's products over reactants for bases producing ions. For Ksp, it's products over reactants when we dissolve a precipitate, so solubility. But again, it's still reactants over products. In this chapter, we're going to talk about Kc, which is products over reactants. Do I keep saying reactants over products? I'm sorry. Products over reactants when we're dealing with concentration. And Kp is products over reactants when we're dealing with partial pressures. So all of these chapters, the format for constructing the equations is exactly the same. It's products over reactants. So I'm going to teach it as one whole unit. Now, one of the things that I advise AP students in particular is to be careful on the AP exam. They love to ask questions about kinetics and how it relates to thermodynamic equilibria, how much product. And the truth of the matter is there is no hard set rule where we could say 100% of the time, hey, this is how reactants and products position the equilibria based upon speed. There are some very slow reactions that produce a lot of product, and there are some very slow reactions that produce very little product. There are some fast reactions that produce very little product, and then there are fast reactions that go to completion. So there is no hard, fast set rule. And one of the things they like to do is they like to give you kinetics data and then ask you a KEQ question about it, and there is no relationship there. There is only one thing that we can say with certainty relating lowercase k, the rate constant, to uppercase K, the thermodynamic constant, is that at equilibria, because both of these represent equilibrium, the speed of this forward reaction is equal to the speed of the reverse reaction. And that's the only thing that we can say. So your book goes on to say, well, you come up with KEQ by taking the rate constant of the forward reaction and dividing it by the rate constant of the reverse reaction, and that's going to give you an indication about your products and your reactants. And that's a true statement, so let's take a look at how that comes about. Get it? Tell a joke about equilibria. K, as in capital K, K-E-Q. Okay. Suppose we're dealing with this sort of reaction. And let's say A plus B produces AB. And at equilibria, we know the rate of the forward, so we'll write rate forward, is equal to the rate of the reverse. Okay, so what does that look like then? Well, all right, rate forward. If we were to write the rate law for the forward reaction, we could say, all right, rate forward is equal to K for the forward reaction. If it was a one-step mechanism, then we could say that that's A times B. So if we look at the reverse process, where we're going from our product here and we're decomposing it back into reactants, then we would say, okay, fine, the rate of the reverse reaction is therefore K for the reverse reaction times AB. So if we work that out and we do some substitutions, and I went ahead here and did it in advance, we'll set the rate forward equal to the rate reverse, so I'll do my substitution. K forward reactants raised to whatever power, K forward products raised to whatever power. If we rearrange that, then we get the rate constant for the forward over the rate constant for the reverse is equal to products over reactants. So in my particular example, let's do this, we'll say KF times A times B is equal to KR times AB. Now I'm going to bring KR over to the left side. So divide both sides by KR. I'm sorry, I'm insulting you, telling you how to do algebra. And then we'll bring A times B over to the other side. Remember, the brackets means molar concentration. So we have essentially here products over reactants. So it does work out. That's where the KEQ expression comes from. It's a relationship among the rate constant for the forward, rate constant for the reverse. Now, we said the bigger the rate constant, the faster that process is. Okay. So why then don't we go to completion? Well, we said, first of all, you create a product. You have the Maxwell-Boltzmann distribution. Those particles aren't all moving at the same speed. If an extremely fast one hits another one, they could break apart and revert back into reactants. So we never get 100% yield. But if we look at the rate constants and we compare it to analogously, let's say a person running a race versus another person, and they're starting on opposite ends of a field and they're running in opposite directions. So we got our little guy here. Look at that, he looks fast, and he's going to be running in the forward direction. And then we got our little guy here, and he's going to be running in the reverse direction. And if they were running at the same speed when we start the race, they would meet right here in the middle. However, if the forward reaction guy was faster and the reverse reaction guy was slow, they wouldn't meet in the middle. This guy would cover more ground, and let's say they might meet there, or they might meet even further along towards where the reactant guy is. And the reverse is possible also. In some reactions, maybe the reverse reaction is thermodynamically favorable, it's faster, and we wind up having the reverse reaction with a larger K value, rate constant value, and let's say they meet there. So equilibria is established where they meet. The speed of the forward equals the speed of the reverse. So you wind up with this position, what they call the position of the equilibria, and it either favors sometimes products or it favors sometimes reactants. In this particular example, if the reverse reaction is really fast, then we would say that this favors what they call the left. And what's on the left of a balanced equation? Reactants. So we're going to wind up with more than 50% of our material being reactants in this particular scenario. So again, it depends upon the rate constant. Okay. With that said, let's get rid of this guy. And let's get rid of this guy. All right, so what did we get out of this? What we got out of this is that, look, the position of the equilibria depends upon the kinetics of the forward versus the reverse reaction. But we're not going to deal with those sort of calculations in this. We're just going to take a look at reactant concentrations and product concentrations. But I want you to understand why they're going to use terms like this favors the products, this favors the reactants, this represents a shift to the left, this represents a shift to the right. When they talk about that position of the equilibria, that's what they're referring to. So let's say we have a reaction like this. Let's do NO2, and 2 moles of NO2 is in equilibria with N2O4. Well, the K for this, pretty easy to write. What you do is you take the product concentration and you put it over the reactant concentration. Now the exponent is the molar coefficient, so this becomes NO2 squared. So let's say we have something like this. We have, at equilibria, we have 12 molar dinitrogen tetraoxide and we have 1 molar nitrogen dioxide. We would say that our KEQ for this is a value of 12. And when you have a number greater than 1 in the fraction, that means your product numerator is greater than your reactant denominator. So we would say that this favors products. We could make a general statement about the position of the equilibria, and we would say this favors products. Now, if you have a very small number, that means your denominator is larger than your numerator, which means your reactants are more numerous than your products. So we would say that that favors reactants. Another thing that we could say, instead of saying favors products, we could say that this favors the right. Why? Because products are on the right-hand side. If it favors the products, we say the equilibria lies to the right. If it favors the reactants, we say the equilibria lies to the left. Now, what determines the value of K is the environment in which we're running the reaction. So other than changing the temperature, that value of K will not change, but the numbers that make up K could. For instance, it's very possible we could run a reaction, and then at equilibria, we could find that this is 48 molar product, and that our reactant is only 2 molar. And when we do that, 48 over 2 squared, we still get a value of 12. So generally, when they talk about the number itself, 12, we would say that this favors products and that the equilibria lies to the right. The position of the equilibria really refers to the actual numbers that make up the KEQ. And in this particular case, at this temperature, there's an infinite number of values that would come out to be 12. And that number represents what the environment can support. The environment can support a 12-to-1 ratio of products over reactants squared in this case. All right, so take a look at another example. I want to focus on this one right here. All right, so we got our reaction. A plus B produces AB. Now, suppose I start with 6 molar A, 4 molar B, and 0 molar product. Well, we know that in order to reach equilibria, this reaction has to start producing products. Once it reaches equilibria, the value of the reactants and products will stay the same. So in this particular case, we know we're going to use some chemical A, and the reaction is 1 mole of A plus 1 mole of B. So whatever amount of A we lose, we're going to lose the same amount of moles of B. And it also produces 1 mole of product. So we're going to gain that many moles of AB. So in this particular example, I said, all right, fine. We run this, and then at equilibria, we wind up with 4 molar A, 2 molar B, and 2 molar AB. So in order to get the value for KEQ, we're going to do products over reactants. KEQ equal to AB over A times B. So now I substitute in the numbers I got. 2 molar for my product, 4 molar for A, 2 molar for B, and I get 2 over 4 times 2, and that comes out to be 1/4, which is a value of 0.25. So I get 0.25 for my KEQ. Now that's always going to be what this particular reaction yields. Now the position of the equilibria, however, the numbers that make it up could vary. For instance, suppose I run a second reaction, and instead of starting with none of my product, what I decided to do was, let's start with 1 molar for AB, and let's start with 2 molar for A, 1 molar for B. Now the change, notice I'm doing plus X for the change. The amount of change is going to be based upon how this thing needs to go in order to reach equilibria. I know based upon the numbers, if I was to substitute in the numbers we start with, I would get 1 over 2 times 1, which is 1/2. That number is too large. The number is going to have to be 0.25. So I can predict that this reaction is actually going to go in the reverse direction in order to reach equilibrium. And we're going to talk about how to do that in a moment, so don't freak out. So in this particular case, my products have to form reactants in order to reach equilibria. So my products go down by X moles, and each of my reactants go up by X moles. Now I did the calculation in advance using quadratic formula to get the values, but the actual amount of change is 0.27 molar. So the products go down by 2.27 molars, and the 0.27 molar, and the reactants go up, and I still get 0.25 out of the deal. So my 0.73 for my products divided by 2.27 and 1.27 for my reactants still gives me 0.25. So that number stays the same. So we would say that the position here lies to the left. It favors reactants. However, the position of the equilibria depends upon the actual numbers that you have that make up that KEQ. All right, so I'm going to introduce something first. Comparing Q and KEQ. When we talk about KEQ, what we're talking about is this is what we're going to have at equilibria. So at equilibria. Q is the same calculation as K, but it's going to be our initial values. So in that last example, my Q was 1 molar product over 2 moles of A, 1 moles of B, and I had 1/2. Well, 1/2 is greater than 1/4, which was the KEQ value. So that means I have too large of a value. Q is greater than K. So when Q is greater than K, the system shifts to the left because you don't have enough reactants there. Because your numerator is, what am I doing here? I must shift left. Yeah, because you don't have Q greater than K. That means ratio is too high. Why am I having trouble with this? Why am I blanking on this? That's why I hate videos, because I can't edit this, and now I'm caught logically and I don't understand what I'm missing here. 0.5, too high of a value. So that means I have too much product. 0.5 is greater than 0.25. And again, a larger value means too much numerator. Your products are in your numerator, therefore you're going to have to take products and turn them into reactants to bring that Q value down to KEQ. I'm sorry about that. So again, if you have a larger Q, that means too much numerator. If your Q is smaller than K, that means too much denominator, too much reactant, and your reaction is going to proceed in the forward direction. So let's say we had something like this. We have a reaction. Let's go back and do our NO2. 2 moles of NO2 produces N2O4, and we know that the KEQ for this is equal to 12. So suppose we say, all right, initially we're going to start with 6 molar NO2, and we're going to start with 1 molar N2O4. What direction will the reaction go to reach equilibria? All right, so we do our Q. Our Q is going to be our initial values. So K for this reaction is product over reactant squared. All right, so we substitute in our product, and we got 1 molar. We substitute in our reactant. We got 6 molar. Let's square it. So we're 1 over 36, which is 0.028. Now our KEQ is 12. So in this case, Q is way less, 0.028, is way less than K, which is 12. So if Q is way less, then that means too much denominator. The denominator is the larger value here, and there's just way too much reactant, way too much denominator. So we're going to have to take some of those reactants and we're going to have to turn them into products in order to reach equilibria. So we would say that this reaction proceeds to the right to reach equilibria. Okay. What is the equilibria expression for the synthesis of ammonia? Okay, so you would need the equation for that. Now, in order to get the actual KEQ expression, you need to do what's called the mass action expression. Now, in the mass action expression, again, we do our products in the numerator, and we raise it to the power of whatever the number of moles are. And then we're going to divide that by the reactants raised to whatever power number of moles are. However, in a KEQ expression, you do not include pure solids or liquids. Let me give you a reason why. We never include in equations things that don't change. If you have an initial value and then it doesn't change when you get to your final value, those two values are going to cancel each other out, so they're not worth including. For instance, when you're dealing with liquid water, H2O liquid, well, H2O liquid does have a molarity, moles over liters. If we had liters, we would wind up with 100 grams. So 1 liter would be, would be 1,000 grams of water, and there's about 18 grams per mole for water. So this comes out to be 56 molar when we do the calculation. So water does have a concentration. That's a very high number. Most of the things that we're dealing with are either 1 molar or usually less than 1/10 of a molar concentrations when we're dealing with a water environment. So if we had a 1 molar value, let's say this reacted by 1 molar, that would only reduce it to 55 molars. So our products water would have a value of 55, our reactant, water would have a value of 56 molar, and that comes out to be 0.98, which is extremely close to 1. So they essentially cancel each other out and have no effect on the position of the equilibria. So pure solids and pure liquids are never included when we do a KEQ expression. You just ignore them. All right. So let's start with generalized KEQ, writing KEQ expressions. Now, KEQ doesn't have to be a chemical reaction. It could be a physical process. For instance, let's say we have 2 different rotamers of C2H6. Now, if we look down the carbon-to-carbon bond, each of these carbons is connected to 3 hydrogens. So if we take the rear carbon and we're looking at it from the front of that atom, we could say at our 109.4 degree bond angle, our tetrahedral bond angle, the 3 hydrogens might be connected like this. Now, we don't want the hydrogens to interfere with each other. They all have negative charge clouds. So I'm going to draw a dot for the front carbon, and that carbon also has 3 hydrogens connected to it. But notice that the hydrogens are in the front carbon are rotated halfway in between the hydrogens in the back carbon. We call this a staggered rotamer or staggered arrangement. And the staggered arrangement is very low energy. Now, when you add heat, the molecule absorbs the heat and rotates the bond to a position of high energy. In other words, we go from a low energy arrangement, you add heat, it absorbs the heat and becomes a high energy arrangement. So the back carbon is still going to look like this. Here's the carbon with its 3 hydrogens connected to it. But now the front carbon, the hydrogens line up in the same position as the hydrogens behind it. And that causes electron interference, which is very high energy. So here's my high energy arrangement. And in my high energy arrangement, the hydrogens are one right behind the other. We call this an eclipse. So we have staggered and we have eclipsed. So maybe at low temperatures, we might wind up with a KEQ for staggered versus eclipsed. Again, it becomes eclipsed. Maybe at a lower temperature, 80% of the particles are in the staggered relationship and 20% of the particles are in the eclipsed relationship, and we would get a KEQ of 0.25. Now at a higher temperature, a lot of those molecules are going to convert and take on the high energy eclipsing arrangement. So our KEQ at the higher temperature is still going to be eclipsed over staggered, but maybe it's now 60% eclipsed and only 40% staggered, so we wind up with a KEQ of 1.5. So remember I said temperature is the only thing that actually changes the number for KEQ. At low temperature, this number was only 0.25. At a higher temperature, the number was 1.5. So you can write anything as KEQ. It doesn't have to be a chemical reaction. It could be any sort of process where we have an initial value and a final value. But most reactions follow what we call the mass action expression, where if you have a chemical reaction, in this case, little a moles of A. So we would put our reactants in the denominator. So here's our reactants, and we're going to put them down here in the denominator. And we're going to raise the concentration of A to the number of moles of A. So big A raised to the little a, and big B raised to the little b. And then on the product side, here's our products. So we're going to put our products in the numerator. And again, big C raised to the little c power. Big D raised to the little d power. So again, they call that the mass action expression. And the only exception to this format is no pure liquids, no pure solids. So we go back to that little question that was on the slideshow. It said, all right, what is the general KEQ expression for the synthesis of ammonia? So we get 3 moles of hydrogen gas plus 1 mole of nitrogen gas. And that's going to produce 2 moles of ammonia. All of these are gases. Now there's 2 ways you can write this. You can always write it as Kc, which means equilibria based upon concentration. So we do the concentration of our products, and we raise it. In this case, we're going to square it because there's 2 moles of ammonia. And we're going to put that over our reactants. So we're going to do concentration of hydrogen cubed. And there's only 1 mole of nitrogen, so we're going to multiply that by concentration of nitrogen raised to the first power. Usually, though, when we're dealing with gases, they like to use partial pressures, so they usually do what's called Kp. And it's the same thing, except for instead of brackets, they use parentheses. A capital P for pressure, so we'd say the pressure of the ammonia squared over the partial pressure of the hydrogen cubed times the partial pressure of the nitrogen. That's normally how you're going to see it, but at this level I would accept Kc or Kp. Now, this no pure liquids, no pure solids thing. All right, suppose we're doing the following acid-base reaction. We're going to take NH4 plus aqueous, and we're going to react it with H2O liquid. That's going to produce NH3, aqueous, and what's called hydronium, H3O plus aqueous. So now we have to set up a KEQ expression for this, and we'll still do products over reactants. So our products are ammonia times hydronium. Notice I did not raise this to the positive power. The positive is the charge on the H3O. That is part of the species. It goes inside the brackets, not outside. But there's only 1 mole of it, so I raised it to the first power over my reactant. So I'm only going to write NH4 plus. And I'm going to ignore water because its concentration is going to essentially stay 56 molar, and the value would cancel out of the expression. So my answer for the general expression of that acid-base reaction is ammonia times hydronium over ammonium. Now, in chapter 23, they talk about KSP, which is dissolving of something. So we're going to take a solid, and we're going to dissolve it, and it's going to produce a couple of charged particles. So, for instance, suppose we are dealing with, let's do lead chloride, solid, and that is going to dissolve a little bit, not much, into lead 2 plus 2 moles of Cl minus, aqueous. Okay, so when we set up KEQ for this, again, we do products. Again, notice I didn't raise lead to the 2 plus power. The 2 plus is the charge. The charge goes in the brackets. The number of moles is the exponent. So when I do chloride, I'm going to square that because there's 2 moles of chloride. Now, I'm not going to include the lead chloride solid. So whenever you have a reactant or product where we have nothing to put into the equation, it actually becomes the value 1. So technically this would be lead 2 plus over chloride over 1, but it's not generally done. It's just like H2O is not H2O1. We just exclude it. So our answer is lead times chloride squared is the K. And since this is the solubility product, notice it's no denominator, so it's not a quotient. They just call it solubility for dissolving product because you're multiplying the positive ion times the negative ion. So we just call it KSP, solubility product. Let me see if there's anything else I wanted to show you as an example. There's a worksheet that I gave you, I posted, that you should try, and then check the answer key on it. But I'm running out of space here. All right, let's try one more. Let's do, I don't know, try to think of something off my top of my head here. What if we did, I don't know. HCl in this case will be a gas. And that ion. And in fact, let's change this a little bit so we make this a little more interesting. In fact, let's simplify this. My goodness gracious, I'm making this harder than this has to be. You know, that is terrible. Let's get rid of, oh my goodness gracious. That's terrible. Okay, now let's just go back and balance this. All right, so there's our equation. What would KEQ for that? 4 moles of disulfur trioxide produces elemental sulfur solid plus 6 moles of oxygen. What is the KEQ? I'll pause and then come back and you check the answer. Okay, I'm back. So again, KEQ is going to be products over reactants. Now we're going to ignore the S8 part of this because it's a pure solid. And we will do partial pressure of oxygen raised to the 6th power over the partial pressure of disulfur trioxide raised to the 4th, or you could have just put them in brackets without the partial pressure. Okay, KEQ calculations. And then what does the equilibria constant mean? Very large versus very small K calculations. Before we do the calculation, I want to address this. If we're dealing with a KEQ value that's less than 1, that means that in terms of KEQ, that means your products are a small value and your reactants are a very large value. So if the value is less than 1, that means that the position of the equilibria favors the reactants and that the position lies to the left. Now, when you have a reaction with an extremely small KEQ, that KEQ value could approach as small as 0. Now, if you have such few reactants becoming products, like for instance, we're going to study some KSP values where you're going to get values like 1 times 10 to the minus 14. So that means one product, 10 to the 14 for your reactants. Why is it worth studying? Well, for instance, when you have lead solids compounds, the lead 2 plus ion dissolves in water. Now, it doesn't dissolve much. It might be a few parts per billion. But those few parts per billion may be enough to cause brain damage. So biologically, even reactions with small KEQs that approach 0, are still worth studying. Now, on the opposite end, if we have a KEQ greater than 1, that means that our product value is very large, just the opposite, and our reactant value is very small. So that means that the products dominate. So we would say that the position of the equilibria favors the products, and that the position of the equilibria lies to the right because the products are on the right side of the balanced equation. And as these small KEQ, really, I hate being left-handed. My knuckle rests against this and causes that to change. As these can approach values of 0, large KEQs can approach values of infinity, and when they approach values of infinity, we don't talk about equilibria anymore. We refer to them as stoichiometric reactions. So when we're talking about very small, that means that the KEQ can approach 0, but they're still biologically worth studying, even though they may approach 0. And for very large, we no longer talk about them in terms of equilibria. If it's very large, it approaches a value of infinity, and it has a stoichiometric relationship. Again, KEQ values less than 1 mean the reactants dominate. The position favors the reactants and lies to the left. And for KEQ values greater than 1, that means the position favors the products and that the equilibria lies to the right. All right, let's try this problem. Okay, that was the best that this program could do to translate my handwriting. So, 2 moles of NO2 produces N2O4. The Kp for this is 12.0 at 25 degrees C, but the Kp for this reaction is only 0.861 at 50 degrees C. First part of the question. At 25 degrees C, the equilibria partial pressure of dinitrogen tetraoxide is found to be 0.214 atmosphere. What is the equilibria pressure of the NO2? Is the reaction endothermic or exothermic? Justify your response. Okay. Let's start with the calculation. First of all, KEQ for this is equal to 12.0, and we know that KEQ for this is partial pressure of the product over partial pressure of the reactant quantity squared. We know the value for the product, so really all we have to do is solve for the partial pressure of NO2. So NO2 squared is going to be partial pressure of N2O4 divided by 12. And we can substitute in, we can solve for NO2. So the partial pressure of NO2 is the square root of the partial pressure of N2O4, which we already know is 0.214 atmospheres over 12.0. All right, so this comes out to be 0.214 divided by 12. I get 0.0178. Let's take that and take the square root of it, and we get 0.134. So this would be 0.134 atmospheres. Now, are there units for KEQ, like there is for the rate constant? And the answer is yes. And here's where the hypocrisy came in, because I said you always have to use units. However, in K expressions, they generally leave the units out, which is why I left the units out in this particular example. We know we're solving for partial pressure of nitrogen dioxide. The answer has to be in atmospheres. So 0.134 atmospheres. Okay, now is this reaction endothermic or exothermic? Well, we're going to talk about Le Chatelier's in the next video, and that'll help with this, but think about it. At the low temperature, the KEQ is a large value. At the higher temperature, the KEQ is a small value. So to get from a large value to a small value, that means the products have to go down and the reactants have to go up. So that favors a shift from products to reactants. So we're going from products to reactants, which is a shift to the left. Now, an increase in heat always favors the endothermic process. However, we have to decide, is the endothermic process the forward or the reverse? In this case, we increased the heat and it favored the reverse reaction. So that means the reverse reaction is endothermic. So that means the forward reaction, which is what they're asking us for, is the opposite, exothermic. And we'll talk about that more about that in the next video. All right, thank you very much.